All right, so Newton's laws of motion, you know them. You like them, hopefully, are really starting to appreciate them in the stuff that we're doing and how it works. His first law, also somewhat known as the law of inertia. And just to sort of give you a definition, because this is another thing that's sometimes very hard for people to define. So I try to write these things down. Inertia is the ability to resist changes in motion or to maintain a state of rest or constant velocity, right? So basically, the more massive something is, right, the more inertia it's going to have, right? Objects maintain a constant velocity, and this is really the core of Newton's first law, that objects maintain a constant velocity, including zero, right? Zero is a velocity. Um, that is just a state of rest, unless acted upon by a force, right? That's the law in itself. And that's where the other half of that, the inertia part, is just, well, the more mass it has, the more it's going to try to resist, or the more difficult it's going to be to get it to change its motion, right? So this is sort of this property that everything has. And I have a video taken from somebody else, but I think it's helpful, so I'll show you. Okay, so this is taken from Veritasium. I'll put the link on the page. I could probably do this one on my own as well, but it's already there, and the video is easy enough to see. So basically, what he's got here is two balls, one basketball, one more of a medicine ball. The black one there you can kind of see is a little bit heavier. He's going to hold them at the same height and let them drop. Um, he's going around asking a bunch of regular people. I will ask you, when he drops both of these balls from the same height at the same time, what should happen? All right, yeah, I think a lot of people would look at the heavier one, particular. It's got more inertia. Let me see if I can play this, and it's going to happen fast. So, okay, what happened? Again, really quickly. So this is not a trick, but really getting ahead to Newton's second law as well, right? Which is this F equals ma. I wrote it in this is kind of the form I try to think about it. A equals F over m. In other words, just look at the A and the F, right? In other words, the more force you have on something, the more it's going to accelerate. Um, and with mass, it's going to be the inverse relationship, right? The more massive something is, the less it's going to accelerate. And that's why F is in the numerator and M is in the denominator of that equation. And usually, though, we just write it as F equals ma. But I think usually, if you're thinking of it conceptually, thinking of it or understanding it as acceleration is probably easier. And of course, for Newton's second law, just because we're talking about it, if there's more than one force acting on it, right, it's just then sum of the forces equals ma, right? Add up all the forces, whatever the net force is, you can treat that as if it's just one force in that direction. Or if you're thinking of it in terms of acceleration. So yeah, with that video, we already sort of got a little bit ahead to the second law as well, because really they're both involved here, right? So if you look at the second law, right, you're saying that the acceleration is proportional to the force. So if you've got more force, it should accelerate more. And if you look at two balls, right, if you've got one more massive than the other, let's say this is big M, and here you've got little m, right, then there's going to be more force on this one. Let's say of gravity. And we can go to that equation too, and I think we will later. But obviously, the more massive an object is, even on Earth, the more the force of gravity is on that object. But if you go to the first law, right, the more massive object has more inertia. And these two things exactly balance each other out, right? So the force of gravity is greater on the more massive object, but also it takes more force to accelerate the more massive object, right? Because it has more inertia. And so those two things balance each other out perfectly here. And they fall at the same rate. So if I were to drop a feather and a bowling ball, what should happen? This is another video I'll link in the course plan or whatever. But yeah, this is exactly that. You can see this is from a Brian Cox documentary thing or something. So this is a bowling ball and a feather. They're both going to drop from a reasonably high height. I think probably something like 10 meters or something. And it's probably you can probably predict what's going to happen. The bowling ball seemed to fall a little more quickly. However, okay, so a little bit later, I think I've teed it up here. What they do, they're able. This is a vacuum chamber. They are able to actually get the air out of here and repeat the experiments. And let's see what happens. They release them both, and slow motion for dramatic effect, I guess, but also so you can actually see them falling. And all the way down. Exactly the same time. And they're very happy. We definitely should be happy, right? I mean, physics works. That's what you want to see. So it is kind of neat to see that in a vacuum. I think they did. I have a link on the course plan as well. When they first did this, I think it was like Apollo 16. I can't remember. I feel bad the name, but they did this on the moon because no real atmosphere there with like a hammer and a feather, and you can actually see that there. So it's kind of a cool piece of history to see them actually trying this and showing that, yeah, it really does work. Um, Newton's third law, I think we talked about that in the last class a little bit. For every action, there exists a reaction force that is equal in magnitude but opposite in direction. Right? In other words, forces always act in pairs. You can't apply a force on some object without technically it also applying that same force on you. And I see I didn't write down anything but had a little space. So I guess the equation, if you wanted to write this, would be F action F reaction in a nutshell, right? So whenever you're using this in problems or something like that, you can write it that way. Here's a picture I pulled from online. Don't know who this some sort of. I put clip art, but that came up and it looked interesting. So use Newton's laws to explain the person firing the shotgun. No, he moves backwards because there is a reaction force, right? Um, so yeah, the fire some, I guess it's shot out of a shotgun, but firing that force, technically, it's exerting a force on the end of the barrel or whatever to propel it forward. So yeah, there's a force, there's an action force for the shot. Right? And you could say this is the force on the shot, and then there's going to be I should try to draw them the same. Right, in the opposite direction. I didn't tee up any videos or set anything up, but you can definitely look on YouTube and see some uh, people kind of discovering this law or not really appreciating this law with shotguns, where they, fire them or do something silly like hold it out with one hand and it flies back in their face or stuff like that. Quite amusing, I guess, if you're looking for some, physics fun or whatever. But yeah, definitely a good case of Newton's third law. Um, and even if you wanted to look at the acceleration of the bullet and everything there, or sorry, the shot in this case, F equals ma kind of happening there too. You could probably even work in inertia there, right? Because you could say, well, the the shot goes pretty fast, right? This goes out here at 100 or over, a couple hundred meters per second, whereas the guy, even the shotgun, doesn't go back as far, right? Because it has more inertia, even though the force is the same on both of them, and the time that the force is applied is exactly equal. But because of inertia, you see a difference there as well. Okay, something hopefully you haven't had to discover in a painful way. That how could we explain using Newton's laws someone trying to step off of a canoe onto a dock but falling short and landing in the water? Well, this is a key here, right? This is what you do. This is how you move, right? You exert a force in one direction on the boat, right? And Newton's third law, that's how you walk, right? You exert a force on the ground, usually. It's not just a canoe like this, right? In the negative direction, and consequently, the ground exerts a force equal and opposite on you. Normally, this doesn't happen though. So, yeah, what exactly is special about this case? Right. So, yeah, I mean, in this case, Newton's second law, the canoe accelerates, right? He's exerting a force on the canoe, and so it accelerates. And just as a side note, right, the ground doesn't normally do this, right? And that's essentially what's happening here, right? Normally, when you walk, you exert a force on the ground, it exerts an equal and opposite force on you. It doesn't move, right? So you've really sort of adjusted when you're learning to walk, if you will, to the amount of force you need to apply to propel yourself forward. But when you're in a situation where the either you can't apply that force, let's say you're on ice or something like that, right? Your foot just slips, it doesn't apply that force. Hard to move when you can't apply the force. Uh, or in this case, you apply the force, but the object you're applying it to is not normal ground and it accelerates away from you. You're not able to apply as much force as you would want to because the object starts moving, right? And then you're not, you don't have the force that you would, and you can't make yourself go forward as you want. And right, since you were depending on the amount of force you could apply to give you an equal and opposite force and let you move forward a certain amount, now sadly that does not happen. All right, so we may be getting a little bit ahead of ourselves with this problem because this stuff's going to come up a bit more later, particularly with apparent weight or whatnot. But I think even at this point we can do it as long as it's just drawing all the forces and setting them equal to ma, right? So here we've got a man inside an elevator that is accelerating up at 2.2 meters per second squared. He's standing on a scale that reads 990 newtons. Now his apparent weight is 990 newtons. We want to determine the mass of a man. So the way I would look at this apparent weight is this is basic. This is what the scale would read. For all intents and purposes, though, this is the normal force, right? The scale might as well just be included as part of the floor, right? Because whatever force the man exerts on the scale, it exerts on the floor, okay, plus its own weight, but whatever. And similarly, then the floor responds with whatever force sent back the other way. And so you might as well just look at the scale as if it's just part of the floor and look at the normal force. So if we draw our free body diagram for the man, right? Maybe a little big, but there's our free body diagram. And so here, like I said, we can take this and say this is the normal force. I'll say exerted by the floor. Slash scale. Right, which is essentially what happens when you step on a scale, right? It's basically the force you're exerting down, it exerts the same force on you because of Newton's third law, and that consequently is how it determines whatever reading. So we've got our man, we know that, and we can draw some of these forces. Now we know we've got gravity going down, and we know we've got some normal force going up. Now here's where, again, I believe a sign convention is always very, very important, perhaps more than ever. Sometimes you just sort of understand it, but I think in a problem like this is really, really important. So anyway, let me just sort of equate these two here, just so I can use them interchangeably. So I'll sort of try to just develop an equation, if you will, and then we can plug in the numbers after. So we know when we sum all the forces in the y direction, that equals ma. So so let's write that. What are all the forces in the y direction? Well, the normal force, which is the same as this apparent weight, which we can write with an r, is in the positive direction, minus Fg equals ma. Fg we've calculated before. We know that's just mg. So we can write r minus mg equals ma. We've got m terms on both sides, so I'm just add mg to both sides. So that will give me r equals mg plus ma. Then I'll factor out the m. And that actually gives me an equation that I can sort of use or tuck in my back pocket if I have a situation like this, right? I'll just say apparent weight formula or whatever here you want. And, we can take a second to sort of think about this. Does this make sense? Well, this says your apparent weight, right? Which normally, remember, normally weight, right, which is just mg, is just, right? So here we're saying when this person is accelerating up, right, we're going to add the acceleration to that. So the apparent weight then is going to be multiplied by a larger number than 9.8, making him heavier effectively, right? Making it a stronger weight. And that should somewhat connect with your experience, right? If you're in an elevator and it's accelerating up, you feel heavier, right? You feel a greater force on you from the ground. So that sort of connects with it. If you were accelerating down, then A would be negative, and then you would be multiplying your mass by a number less than 9.8, because it would be 9.8 minus the acceleration, and then your apparent weight would be lower. And that should also connect with your experience in an elevator, right? When it's accelerating down, you feel a little bit lighter as it's accelerating, right? Then it gets to a constant speed and it doesn't matter, right? Then while it's moving at a constant speed, you feel exactly the same way you feel when it's stationary, right? Because that's also a constant speed. So for this, we can actually, now this question asked about the mass, so I can rearrange this equation for mass, which basically means I can divide both sides by g plus a. And if I substitute in the numbers, R was 990. And 9.8 we know, plus 2.2. So that is 990 divided by 12. And that means the mass of the man is 82.5 kilograms. Yeah. Compare that with what the mass would have been if it wasn't accelerating, right? It would have been higher than that. All right, for our last example here, We have a student sits on a chair with a well-greased wheels. Basically, just there's no friction you have to think about. The combined mass of the student and the chair is 80 kilograms. 5 people all push the student. Ali pushes with a force of 100 newtons north, Bronson with a force of 150 newtons east, Cece 200 south, Dana 350 north, and Ellen, I don't know, 50 north. Determine the student's acceleration. This actually goes back a little bit to one of the homework questions we were looking at, where you have to consider, the net force. That's really what matters, and that's a big theme of, the any physics course, right? That it's the net force that determines the acceleration. Whether it's 5 forces that all act together to make a net force, or it's just one single force, doesn't matter. So let's sketch this out just so we have a little bit of an idea of what's actually happening here. So this will represent, here's our 80 kilograms, right? There's our 80 kilogram box that represents the student and the chair. We don't have to worry about any up or down, so we'll just use, our standard, let's say, here's our positive, right? North and east is positive, which I'll use as X and Y as well, but, So now I can go through the forces. Someone was very nice, and they even named them basically A, B, C, D. That was really thoughtful whoever wrote this question. So we've got A, 100 newtons north, which I can just draw in here, and B with a force of 150 east. Suppose I could at least put newtons here. C 200 south, and D 350 west. Let's move that up a switch. And E 50 east. Let's see if I can. Just to sort of represent all of those there. So we want to determine the student's acceleration. So that means we need to figure out the net force. Right? These are all vectors. So we'll look at each dimension independently. Which one we do first doesn't really matter. Let's look in the X direction. And we know that in the X direction, right, the sum of all the forces in the X direction equals MA. So we've got positive 150 plus another positive 50. That's those two right there. And then we've got this in the negative 350, or 350 in the negative direction. So minus 350. MA. And in this case, MA, we know the mass is 80, right? So that's just 80 times the acceleration. And I'll just put a little subscript there to let you know that that is in the X direction, right? So that gives us 200 minus 350. So that gives us minus 150 equals 80 A in the X direction, which means A in the X direction is just equal to negative 150 divided by 80, which I believe is 1.875, or negative. And, or you could write this, right, just because we're using our directions here, you could write that as 1.875 west. We can do a similar thing in the y direction. We can say the y direction, the sum of all the forces in the y direction equals ma in the y, and I guess I could have put in an x up there as well. And in the y direction, we've got positive 100 and minus 200. That's these two forces up there. And that has to equal the same mass, but now a in the y direction. 100 minus 200 is just negative 100 equals 80 AY. Divide both sides by 80, and that gives us a y equals negative 1.25, or 1.25 south. Although in this case, yeah, using it as like south and west, it's okay. But now we can put Humpty Dumpty back together again, and we can look at, well, what is the total acceleration, right? We have the two components of the acceleration, so we can put them together. We can say there's my 1.875 in the west direction, and I need to add to that 1.25 in the south direction. So here's a x. And this then here, I'll just make, right, this is the actual total acceleration here. I'll put an angle here as well. And again, just understanding when I do get an angle like that or draw an angle like that, I have to understand that that angle is from west toward south. So I can get the magnitude of the acceleration now with Pythagoras. That's going to be 1.875 squared plus 1.25 squared. And if I work that out in my calculator, I get 2.25. And also I can say the tangent of theta, and I usually do go back this far and just look at the actual angle and say, okay, I need the opposite side, and then I have to divide by the adjacent side, so that's 1.25 on top, just so I'm careful. 1.25 divided by 1.875, that means theta equals the inverse tangent of 1.25 divided by 1. And if I do that, I get 33.7. Therefore, the acceleration is 2.25 meters per second west, 33.7 degrees toward the south.